Okay, Bridge 1 students, we're going to do a deep dive on the deductive today. That means deductive reasoning. And the reason I say that is that the old high school geometry class, about 5 years ago, was blown up and pushed mostly down into Math 2 and Math 1. And that old class was an interesting class. It was a mix of technical math skills, spatial reasoning, and then almost a humanities class on deductive reasoning built into it, which really in some ways was at the heart of high school geometry, which by the way is the oldest class that high schoolers take. It's based around a set of ideas proposed by Euclid 2,000, maybe 200 years ago. So very old ideas and very powerful. So my objective, big picture, since we have just a short time, is to focus on that, looking at deductive reasoning and making improving geometric claims, really looking at that in depth. But there's also a specific objective I have for this lesson, which is that students can understand the measure of angles formed by intersecting lines. Okay. So I want to start with kind of a philosophical issue. This is the idea of an axiom. An axiom is something that we simply assume to be true, and this one is really old. In fact, it was called Euclid's fifth postulate, as recast through a guy named Playfair, a mathematician named Playfair in the 1800s. You hear Cato barking there. It says, through a point on P, not on line L, there is exactly one line parallel to L. I'm going to see if I can draw it here. I'll draw it in pink. What do you think? There? I was going to cross, right? There? I'm going to do my best. Well, it's almost not through P, but that's pretty close to parallel. And that's the idea. It's interesting. This postulate here is debated. It's one of Euclid's postulates that's heavily debated. But for our work here, we're going to assume it to be true. And I think that's important because as we talk about deductive reasoning patterns, we have to really look at things that we assume to be true and then things that we have proven to be true. Okay. So we've already worked with this a good bit, and I'd like you to think back for a sec to the following lesson, and that lesson is 16.4. That was a lesson that we did last term or second term on deductive and inductive reasoning, and you may remember that there was a whole bunch of properties that we looked at, memorized, wrote down in our math notes. Those included, among other things, the addition and subtraction properties of equality, multiplication properties of equality, transitive properties of equality. Hopefully you guys remember those. We talked about the linear pair theorem. There's a couple other items there. It's really worth looking back at lesson 16.4. It's going to help you. Okay, so right now, for our lesson, we're going to look at lines actually that, unlike this set of parallel lines here, this pair of parallel lines that never cross, we're going to be looking at lines that do cross. That's the theme for our lesson in the book today. And we're going to look in particular at proving something called the vertical angles theorem, which says that if you have this situation you see here, and we assume that angles 1 and 3, I'm going to mark them out here. Here's 1, and here's 3. Those are vertical angles. We need to prove that angle 1 is congruent to angle 3. In the past, you've just been told that. And the kind of exciting thing about geometry here at the high school level is that we're going to actually prove that that has to be true by a series of logical steps. And here we go. Okay. So statement number 1 is angle 1 and angle 3 are vertical angles. And that's given right there. So we just would write here, and I encourage you to write this down. This is called a 2-column proof. It's basically a T-chart to help us keep track of our logic. So that's given. We also know that angles 1 and angle 2 are what are called a linear pair. I'm going to encourage you again to look at lesson 16.4. What's called the linear pair theorem is discussed in lesson 16.4. Here, using a different color, maybe I'll do, I don't know, this color, purple. I just want you to see that angle 1 and angle 2 together make a straight line. Okay, so that's basically what it means that that there's a linear pair. They also share this ray right here. Okay, so angle 1 and angle 2 are supplementary, and I just gave you the name actually of that theorem that would tell us that. If you remember, that's called the linear pair theorem. I apologize for my bad handwriting here. I'm learning my new technology. Okay, so according to the linear pair theorem and what's called the definition of supplementary angles, what do we know about supplementary angles? What do they add up to? You may recall that by definition, supplementary angles add up to 180 degrees. So that's going to snap in place there. I love it how it does that. Measure angle 1 plus try this. The measure of angle 2 sum up to 180 degrees. In other words, once again, looking at this purple arc here, those two angles 1 and 2 add to 180. Okay, so some teachers wouldn't allow you to do this, but I'm just going to say for step 5, by a logic analogous to steps 2 through 3, we can say that the measure of angle 2 plus the measure of angle 3 also add up to 180. So I'll do a whole different color there. Maybe, I don't know, green. So 2 and 3 together also make a straight line. That's pretty interesting. And they add up to 180. So let's go down here. The next step is we're going to say that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. And you could say, looking at the picture, that, well, they both add up to a straight line, right? 1 and 2 add up to a straight line. Here they are. 1 and 2 add up to a straight line. And 2 and 3 add up to a line. Or you could look at the algebra here and say that 1 and 2 equal 180 degrees. 2 and 3 equal 180 degrees. And what this is called, when we have two things that equal the same thing, that equal another thing, is called the transitive property. A beautiful property that actually also goes all the way back to Euclid. It's his first common notion. Things that equal the same thing equal each other, is what he said way back in the day. Really interesting that we're still with Euclid in a way. Okay, so we have, now we can say that since the measure of angle 1 plus the measure of angle 3 equals the measure of angle 2 plus the measure of angle 3, if we just take away or subtract the measure of angle 2 from both sides of that equation, we are left with the measure of angle 1 equals the measure of angle 3. And here, you may recall from lesson 16.4 that this is just called the subtraction property of equality. And then we just at the end say that the angle 1 is congruent to angle 3 by the definition of congruence, which essentially says that if the two angles measures are equal, then the angles are congruent. We are done. We have proved what we set out to prove, which is that those two vertical angles by mathematical deduction have to be congruent. Okay, I'm going to be giving you a lot of practice through Khan Academy and through my HRW on specific problems related to this lesson. But again, my big picture goal is really for you to understand the deductive reasoning patterns that are at the heart of geometry. All right, thank you.